So the first thing that I want to talk about, it's 11.10. It's on Taylor and Maclaurin series. It just it's like a power series, but it's like a special case. Oh. And we're going to talk about how to find the Taylor series. Is this on a quiz? No, it's not. So not today's quiz. We're going to talk about how to use Taylor series to represent a function that we could not find the power series from what we did last time. For example, if we have the classical example would be f of x equals e to the x. This function, we cannot turn it into 1 over 1 minus capital X. We can't do that. It's also difficult to find integrals or derivatives in the form that will give you e to the x or d dx of 1 over 1 minus x, or integrals of 1 minus x dx. None of this works. So the trick that we did last time doesn't work when we try to find the power series representation for e to the x. So we need a new technique. But before we do that, let me start with the power series. So consider power series representation for f of x. Let's see, the representation is sigma n from 0 to infinity cn x minus a raised to the power of n. So this means the power series is centered at, so power series is centered at x equals a. So that's what this part tells you. That's just a definition. So let's consider this power series, and I'm going to expand it. So f of x is equal to sigma n from 0 to infinity cn x minus a raised to the n. And if we expand it by plugging n equals 0, n equals 1, 2, so on, we can get c sub 0 x minus a to the 0, which is 1. We just get c0. Plus, if we plug in n equals 1, we get c1 x minus a to the first power plus c2 x minus a squared plus c3 x minus a cubed, and so on. So the question is, how do we find c0, c1, c2, c3? Is there any tricks that we can find them for a given function or c0? Well, the trick is, yes, that you can actually come up with a formula for that. That's what makes a Taylor series special, because there's a certain formula that we can write that will give us a coefficient c0, c1, c2, c3. Let's just kind of go through it, how they come up with a formula for the coefficients. The trick they use is that, suppose we have f of x in this expansion. If we plug in x equals a, so plug in x equals a, what happened is that we get f of a is equal to c sub 0 plus c1 x equals a, so that will be a minus a, which is a 0, plus c2 and a minus a squared, plus C3 a minus a cubed. So when we plug in 0 there, when we plug in a for x, we get 0 for all those terms except for the first term. And then we just end up with f of a equals C0. So C0 is actually the y value when x equals a in the given function. So that's how they come up with C0. Now, what about C1? Can we find C1? The trick is that if you take the derivative of f of x, you get f prime of x, which becomes, when you take the derivative, the C0 becomes a 0, right? So that's gone. And if you take the derivative of C1 x minus a, you just have C1 x minus a give you 1 when you take the derivative. Plus, when we take the derivative of C2 term, so we get 2C2 x minus a, and the plus 3C3 x minus a squared, and so on. And then to find C1 here, because C1 doesn't have any x attached to it. So again, if we set x equals a, so if we plug in x equals a, just like we did before, all the terms with x minus a will become 0. So we just end up with f prime of a is equal to C1. Because all the terms with x minus a in the parentheses becomes 0 when we plug in a for x. And then, so that's good. So we found C0, C1. What if we continue this pattern? Right? So if we continue this pattern, take the derivative again, so we get the second derivative of x is equal to C1 will become 0 now when we take a derivative again. And then 2C2 x minus a will just become 2C2. And then the 3C3, that will become 3 times 2, because when we have to bring the exponent in front. So that becomes 3 times 2C3 x minus a plus the rest. And from here, if we, the trick is again, plug in x equals a. All terms become 0 except for the 2C2 term. So we get f double prime of a is equal to 2C2. And then from here, we can solve for C2. So we get f double prime of a divided by 2 is C2. That's how they've come up with the formula for C2 there. And what about C3? Well, the trick is just keep doing this process. So we get f triple derivative, the third derivative of f of x. That becomes 2C2 will become 0 because it's a constant. And then we have 3 times 2C3. And then plus all the terms that I'm not writing out, they all have x minus a squared. They all have some factor x minus a in them. So if we plug in x equals a, and then they all become 0 except for the constant term at the beginning. So we get f third derivative, the third derivative of f at a is equal to 3 times 2 times C3. And then that will give us C3. So C3 is equal to the third derivative of f with a as an input divided by 3 times 2.
A little confused on how you found C0 and C1.
Find C0 is you take the expansion of f of x. So you take f of x with the expansion here, and then you plug in x equals a directly. When you do that, you end up with f of a equals C0 plus C1 a minus a, C2 a minus a squared, and so on. And a minus a is 0, so all the terms become 0 except for the C0 left. So f of a equals 0, equals C0. And then to find C1, you take the function f of x, you take derivative. You get f prime of x equals C1 plus 2C2x minus a plus 3C2 and so on. And then you, again, just like the previous step, plug in x equals 8. That will give us f prime. That we give f prime of a is equal to C1 plus 2C2 a minus a plus 3C3 a minus a squared and so on. So again, you get this a minus a in all the terms except for the very first term, C1 there. So that becomes 0, and that will give us f prime of a equals C1. And then repeat the process, taking the derivative, plug in x equals a, then we can come up with a formula for C2 and the C3 and C4 and so on. So it turns out that, let me rewrite this, the terms, the expressions I put in boxes, let me rewrite them. So at this point, we have C0 equals f with a as an input. C1 equals f prime of a. C2 equals f double prime of a divided by 2. And the C3 equals f triple prime of a divided by 3 times 2. And it turns out that if you repeat this, C4 will equal to f to the 4th prime of with a divided by 4 times 3 times 2. And this pattern continues. And the C5 is equal to f to the 5th derivative. And normally we write as a parentheses with a little 5 in it. So that means 5th derivative. And 5 times 4 times 3 times 2. And continues. And it turns out that all those terms, even though they don't have a 1 in the denominator, we can just add multiply by 1 in the denominator without changing anything. Except for the C0, obviously. You can think about there's a 1 as well. So what's the benefit of adding the 1 in the denominator to multiply with the rest? Well, that just gives the denominator a factorial. For example, C5 will become f with 5th derivative and a as an input divided by 5 factorial. C4 will be f 4th derivative with a as input divided by 4 factorial. And the C3 will be f 3rd derivative a divided by 3 factorial. And the C2 will be f 2nd derivative with a as input divided by 2 factorial, and the C1 will be f prime of a divided by 1 factorial is just 1. And C0 will be f to the 0th derivative, just f itself, divided by 0 factorial, that's still just 1. So that's a pattern. And it turns out that all the coefficients C0, C1, C2, and so on, Cn will just be f with nth derivative with a as input divided by n factorial. So that's how they come out with this coefficients. I'm sure it's not easy when they figure it out in the beginning, but that's a formula that we can use to find the coefficients for each term in that series expansion. So that's what gives Cn. Now, what's the benefit of this? Well, if we have a formula for Cn, remember that earlier we had f of x equals the sigma expression, right? The power series expression, and we can just substitute for Cn in that expression there. So let me write this. So recall that f of x is equal to sigma n from 0 to infinity Cn x minus a to the n. Now we know what Cn is. We can just put into that formula, and that will give us f of x equals sigma n from 0 to infinity. Cn will be f of n's derivative, the n's derivative of f of a as input, divided by n factorial, and then multiply by x minus a to the n. So let me note that this means nth derivative of f x. That's what that means. So as you can see now, for any given function f of x, right, we can try to use this approach to figure out the power series, even though the previous trick that we talked about yesterday didn't work. But now this will be a new formula that we can try to find the power series representation. And if I expand this now with n, so that will become, so when n equals 0, I get the 0's derivative, just f of a, divided by 0 factorial is 1, right? Times x minus a to the 0, which is also 1. So just get 1 there. So we get f of a. That's the first term, the C0. Plus, if we put 1 there, it will be f to the first derivative. So that's f prime with a input, divided by 1 factorial, which is just 1. I'm not going to write the 1 in the denominator. You can write as 1 factorial if you like, but you don't have to. And then x minus a to the first power. And if we put n equals 2, so we get f to the second derivative of a, divided by 2 factorial, again, it's just 2, x minus a squared. And then the third derivative of a, 3 factorial, x minus a cubed, and so on. So that will be the series representation of a given function f of x. And then this is what we call the Taylor series expansion. Of f of x at x equals a. So we expand the function at a given x value a. So whenever you see someone talk about Taylor series expansion, you know what they talk about. They talk about this expansion. I'm going to go through a couple examples. I'm going to go through one example now to show you how to get this. So, for example, the question is, find Taylor series expansion of f of x equals e to the x at x equals 2. So this is the question. So when x equals 2, what is the Taylor series expansion of this function e to the x? I'm going to use the formula here. So at x equals 2, f of x equals e to the x will equal to, the first term is f of a, right? What is f of a? Well, f of a is just e to the a. So that will be e to the a. And what is a? A is 2 in this case, will be e squared. So that will be the first term. Now, plus the second term is when n equals 1. So that will be f prime of a. What is f prime, first of all? F prime, so note, f of x equals e to the x. F prime was also e to the x, right? So f prime of a it's just e to the a, and the a in this case is 2, so we get e squared. That's f prime of a. We get e squared. Divided by 1 factorial is just 1. And the x minus a is x minus 2. I'm going to erase this in a second, but this is the second term. F of a is the first term. And what about the next term? The next term, the numerator is f second derivative with a as input. Now f prime is e to the x. What about f double prime? That's also e to the x. And if x equals a, that will be e squared again. So plus e squared divided by 2 factorial, and then x minus a squared. So that's x minus 2 squared. And the next term will be f triple derivative, the third derivative of f. So that will be, again, e to the x, just give you e to the x. You take the derivative no matter how many times you take it. So that will be e squared over 3 factorial, x minus 2 cubed plus. And there's a lot of terms coming after that, but for now we can just stop there. Because the rest just follow the pattern. So this expansion here, this is what we call the Taylor series expansion of e to the x at x equals 2. It's very important to notice that here, this is one expansion at a given x value. If we pick a different x value, we're going to have, even though the pattern of the series looks similar, but the values will be different. So x equals 2 is sort of, the value 2 is important when we try to find the Taylor series expansion. Any questions on this exercise? So for those of you interested in taking another math class after this, or even physics class, like advanced physics, you should definitely pay attention to Taylor series. It's going to show up in a lot of areas. So that's the expansion when you try to expand a function that at any x value, x equals a. So a could be any number. Any questions? Now, before I move on to another example, so here's a special case of Taylor series. So special case of Taylor series. So Taylor series is for expansion of function at x equals a, but what if x equals 0? So Taylor series expansion at x equals 0, not just any a. Here, the a equals 0. That's a special case. So what's the expansion? Well, that's easy because we already have the expansion expanded out above, right? I'm just going to take it and then substitute 0 for a. I mean, substitute a with a 0. So that will give me f of x is equal to, from above, so that will be sigma n from 0 to infinity. Let me use a different color. And we have f with n's derivative It used to be a as input, but now just becomes 0 to be the input. Divide by n factorial, x minus a to the n. Right, that's what we had before. But what is a? A is 0, so x minus 0 to the n. Well, when you subtract a 0, you don't subtract anything, just become x to the n. So that's the special case. And if we expand this, we will end up with f of, instead of f of a, we get f of 0 plus f prime with 0 as the input, divided by 1 factorial, just 1, x minus a, just x. And then plus second derivative with 0 input, divided by 2 factorial, x squared. We don't subtract a anymore because a is 0. I mean, we still do, but we just don't keep minus 0 there. And then f third derivative, 0, divided by 3 factorial, x cubed, and so on. So this is the new, it's not a new series, it's still Taylor series expansion, but we give it a new name. So this is called Maclaurin Series expansion. Maclaurin Series expansion. You can just call it Maclaurin Series. It's just a special case of Taylor series with the a being 0. So it is a Taylor series expansion, but with x equals 0 or a equals 0. It's the expansion at x equals a, which equals 0. So if you forget about Maclaurin series, you don't know what it looks like, just think about its Taylor series, and the a in that Taylor series expansion is equal to 0. We expand it at x equals 0. Any questions about this? I guess you can call it definition, not really a definition. So here's an exercise, which is find Maclaurin series of f of x equals e to the x. So here we don't have the we don't just say, oh, we expand this about x equals 0. Because when we see Maclaurin series, we already know it's expanded at x equals 0. So we're just going to use the Maclaurin series. You can use Taylor series we had before, but now it's just a equals 0. So f of x will equal to f of 0, which is e to the 0. And we already know e to the 0 is 1. Plus f prime again is still e to the x, but if we put 0 for x, we get e to the 0, which is 1, plus 1 over 1 factorial times x, plus the second derivative with 0 as an input. So there's still e to the x with a 0, so that's 1 over 2 factorial x squared, plus the third derivative with 0 input, they still get 1, divided by 3 factorial x cubed, and so on. So that is just going to be 1 plus x plus 1 over 2 factorial x squared plus 1 over, you can write as x squared over 2 factorial plus x cubed over 3 factorial, so on. I didn't write down the 1 factorial in the second term, but there's a 1 factorial there. It doesn't matter, just 1. And of course, we can try to use sigma notation if possible. So in this case, it is possible to use sigma notation. So that will be sigma n from 0 to infinity. And if we go back to this form, the one in blue, and we can try to figure out what f in the, because since this function is special, e to the x, so f to the nth power, it's that, sorry, f to the nth derivative, it's always going to be e to the x no matter what. And if we plug in 0 there, so f to the nth derivative of 0 is always going to be e to the 0 equals 1. So that part doesn't change. So that will just becomes 1 over n factorial x to the n, which is if the same if we expand it. So that's a Maclaurin series. Any questions? So here's another example. Let's see, find. Oh, before I talk about another example, this is the expansion of f of x equals e to the x. Right? Now, what if it says, so from here, we can find the expansion, the series representation for e. So to find, notice, we can find series representation for just e for e, which is just e to the first power, right? And you can think about that's like taking e to the x, but set x equals 1. So to do that, we can take series representation for e to the x, but set x equals 1. That will just give us e. So that will just be e equals 1 plus the x will become 1 plus 1 squared over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on. And then that will just becomes sigma n from 0 to infinity 1 over n factorial, because x to the nth power is just 1 all the time. So this is the sort of like the special series for e. Now, another exercise I was thinking about earlier is we can find Maclaurin series representation of sine x, so f of x equals sine x. Because sine x, we cannot use the trick we did before to find out the power series representation. But we can try to find it using the Maclaurin series or the Taylor series. So this implies that we're expanding the function at x equals 0, not just a random number a, it's at x equals 0, because it's a Maclaurin series. That's what I'm looking for. And again, let me copy down the general Maclaurin series. So f of x will become sigma n from 0 to infinity, f to the nth derivative with 0 as input divided by n factorial x to the n. And if we expand it, we get f of 0 plus f derivative of 0 divided by 1 factorial x plus f second derivative at 0, 2 factorial x squared plus the rest. So for sine x, so for f of x equals sine x, when we find the Maclaurin series for this function, f of 0 will be just sine 0. And then the derivative of sine, which is cosine, evaluated at 0 divided by 1 factorial times x. So be careful here. So the 0, x equals 0, I'm not going to plug in this x or x squared or x cubed. So those x squared, x cubed stays the way it is. The 0, we're only going to plug into f, the very beginning. We're only going to plug into this, the f to get the first term. And then we're going to plug in the first derivative to get this coefficient, and then plug in the second derivative to get that the third coefficient. But all the x squared, x cubed, they stay the way it is. You don't plug in 0 there. So that's so f equals sine, f derivative equals cosine x. But what about the second derivative of f? So think about the third derivative and the fourth, the second, third, and fourth derivative of sine. Well, the first derivative is cosine. The second derivative will be the derivative of cosine. So that will be negative sine. That's the second derivative. So that will give us a third term, the coefficient of the third term. So that will be negative sine 0 divided by 2 factorial x squared. And then the next term will be the third derivative of f, which is the derivative of negative sine, which is negative cosine x. So we get negative cosine of 0 divided by 3 factorial x cubed. And if I want to continue the fourth derivative, I'm going to put this notation, the fourth derivative, which is the derivative of negative cosine, which is when you take a derivative of cosine, you get negative sine, but you already have a negative, so that becomes positive sine. So we get sine 0 divided by 4 factorial x to the fourth power. And continue. And we can simplify each term there because we know what sine 0 is, right? Sine 0 is 0. So that becomes 0. This also 0. And this is also 0. And what about cosine 0? Cosine 0 is equal to 1, right? So we have 0 plus 1 over 1 factorial x. So I'm going to write that as, so 0 plus x over 1 factorial. And then plus 0 times x squared, that's a 0 again. And then plus the next term, which will be negative 1 over 3 factorial times x cubed. So you can write as negative x cubed divided by 3 factorial. And the next term is 0. The next term is not going to be 0. So it turns out that sine x, when we find the Maclaurin series or the Taylor series expansion at x equals 0, either way to see it. So that becomes x over 1 factorial, just x, I'm going to write out 1 factorial just in case you want to know. And then the x squared becomes 0, but the x cubed is not. So minus x cubed over 3 factorial. And then the following term is actually plus x to the 5th power over 5 factorial. And then the next term is minus x to the 7th over 7 factorial, and it continues. So it's helpful if you try to remember this. It will be useful in the future when you need it. Any questions about this example? So when you, the thing about finding the Taylor series expansion or the Maclaurin series, it's that you just have to, it's really not that challenging. Obviously, you have to know what the formula looks like, right? But in the formula, if you want to use it, you have to be able to find the derivative. So you just take the first derivative, take the second derivative, the third one, the fourth, because those will help you to find the coefficients for each term there. And if you have a complicated function, you have to be very careful when you find the derivative. It's really, the process is know what the general formula look like, okay. Find the derivative, plug in the specific x value, find out the coefficient, and then put into the formula. Any questions on this? So that's a sine. And we can also find cosine of x, the Maclaurin series. And I'm not going to do it in step by step, but you can also look it up, right, on the internet. And I believe that will just be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so on. So it turns out that the terms from sine and the cosine, if you just forget about the negative, you just take all the terms, swapping the negative sign in front of them, they are all going to be the terms in the e to the x expansion. And then that, it will be another interesting project for you to look into. That's because e to the I x, you can write as cosine x plus I sine x, because they're related to e to the x. That's why the Maclaurin series for sine and the cosine, they're similar to the one for e to the x. Any questions on the examples we have looked at so far? I'm not hearing any questions. All right, so let me do a quick example of another function, and then we can stop here. So find Maclaurin series for f of x equals x times cosine x. So for this function, we want to find the series expansion for it. And again, it's a Maclaurin series, so it's the same thing as saying finding Taylor series expansion for this function at x equals 0, the equivalent. So we're just going to follow the same pattern. So here f of x equals x cosine x. Right? And then when we expand it, the first term will be f of 0. So that will be 0 times cosine 0. That's a f of 0. That's the first term. Plus the second term will be the derivative of f evaluated at 0. So I'm going to write down this, but I'm going to erase it. So this is the f prime of 0 divided by 1 factorial times x. Right? That's the second term. But I need to know what f prime of 0 is. So f prime of x I can find by taking the derivative. So if you recall the derivative, so x cosine x, that will give me 1 times cosine x plus x times negative sine. So that's a minus x sine x. So that's the first derivative. So if I put in here, I have, remember we plug in 0 for x in the derivative. So that will be f prime of 0. Sorry, that will be cosine of 0 minus 0 times sine of 0. And divide by 1 factorial times x. And we're going to find the next term. The next term, we need the second derivative with 0 as the input, divided by 2 factorial times x squared. So I need the second derivative. The second derivative we can find it from first derivative. So the cosine give me negative sine x minus, and then the x sine x, when we take the derivative, we get sine x plus x times cosine x. And then that will become negative 2 sine x minus x cosine x. So that's the second derivative. We're going to plug in 0 for x. So that will give me negative 2 sine times 0 minus 0 times cosine of 0 divided by 2 factorial x squared. And then the next term, I'm going to do it one more term, then I'm going to stop in this series. So the next term is we take the derivative again. So we get negative 2 sine become cosine x minus x times cosine x. We already know the derivative, which is cosine x plus x minus x sine x. And if I simplify this, so that will become negative 3 cosine x plus x sine x. So if I need to put 0 in there in order to find the next term in the Maclaurin series. So that will be negative 3 cosine of 0 plus 0 times sine of 0 divided by 3 factorial times x cubed, and so on. So that's sort of like the that's following the pattern, right? The expansion of Maclaurin series. We just find the f of 0, f prime of 0, f second derivative of 0, and so on. The rest is about simplifying. So I don't need this work. This is just sort of scratch work on the side. To simplify, cosine 0 is 1. But times 0, that gives me a 0. So the first term becomes 0. And the cosine 0 is 1. And the 0 times sine 0, that's a 0. Sine 0 is 0. 0 times cosine 0, that's also 0. Now cosine 0 is 1. And that's a 0. So it turns out we have 0 from the first term. And then 1 over 1 factorial times x. The x squared term becomes 0, but the x cubed term becomes -3 over 3 factorial x cubed, and so on, and the rest. So this becomes x minus, if we simplify the 3 over 3 factorial, so 3 over 3 factorial, that becomes 3 over 3 times 2 times 1. That's a 3 over 2 factorial, or you can write as 3 over 2. Oh, sorry, 1 over 2 factorial. So that's a 1 over 2 factorial x cubed, and the rest. But this is the Maclaurin series for f of x equals x cosine x. All right, questions about this example here, or any of the examples I have done earlier with Taylor series or Maclaurin series?
Could you explain how you got the big fractions again?
The big fractions, do you mean those, the coefficient? Yeah. Right, so this expression should be f prime of 0 divided by 1 factorial, right? And what I did is on the side, I take the function f of x, I find the derivative f prime of x, just normally, you know, how we take the derivative. But I need f prime of 0, not f prime of x. So what I did next is I plug in the derivative, I plug in x equals 0, and to find f prime of 0, which is just plug in 0 for each term there, cosine 0 minus 0 times sine 0. So that's what f prime of 0 is. And I just put it in the numerator there. Same thing with the next term. The next term, this coefficient is f second derivative with 0 as an input divided by 2 factorial. So on the side, I found the second derivative by taking the derivative of the first derivative. And I end up with this being the second derivative. But I don't want the second derivative. I want to find the second derivative with x equals 0. So I plug in 0 there. And then that gives me f second derivative with a 0 as an input. -2 sine 0 minus 0 cosine 0. And then I take that expression, put in the numerator, and it repeats this process.
You always have to plug in 0?
When we find the Maclaurin series, we always plug in 0. When we find if it just say find the Taylor series expansion at x equals 5, right? If it's not finding Maclaurin series, if it just say find the Taylor series expansion of this function, same function, at x equals 5, so you will be plugging 5 into the derivatives to get the coefficients instead of plugging 0. And then you have to, instead of writing x, you will be writing, maybe I'll just write down quickly. So let's take since we already have a derivative, right? So if it says find Taylor series expansion of f of x equals x cosine x at x equals 5, if that's the case. That's a question, right? So for Taylor series, it's the same. So f of x will equal to the first term is f with the input. The input is 5 here. This is the a value. So f of x will be f of 5. And then the next term will be f prime with a is 5, divided by 1 factorial times x minus a, x minus 5. So that's the difference. So this part will be different. Obviously, this is different value. And also this part is different. It's not -0. If it's -0, you just have x, but it's -5. And then the next term will be the second derivative, but with 5 as an input, divided by 2 factorial x minus 5 squared, and so on. So that will be, I'm just going to do it quickly, plug in those values. So f of 5 will be 5 times cosine 5 plus f prime of 5. So that will be, I'm just copying the f prime from earlier. So that will be cosine 5 minus 5 times sine 5 divided by 1 factorial times x minus 5 on the side. And the plus, the second derivative, again, I'm copying on the derivative, so that's a -2 sine 5 input minus 5 cosine 5 divided by 2 factorial x minus 5 squared. And it continues. So it's not easy to simplify because cosine 5 is not a nice number, right? Sine 5 is also not a good number. So it's not, we just leave it. Or if we have a calculator, we can estimate the coefficients, but I'll just leave it. Okay, like I said, I want to spend a few minutes going over any final questions you have from the homework. Any other questions about Taylor series or Maclaurin series? All right, if we don't have questions, any questions from the homework or from studying for the quiz? All right.
I have one.
Okay, go ahead.
I'm just kind of confused on why this one's conditionally convergent. So if we go over it, it's sigma infinity to n equals 1, and then parenthesis -1, and parenthesis n minus 1 over root n.
This one?
Yeah.
So I guess the question is asking to determine if this is conditionally convergent or absolutely convergent or divergent. I suppose that's a question.
Yeah.
So I'm going to treat as if I don't know it's conditionally convergent. Right? I'm going to try to decide if it's absolutely convergent. There's a couple of ways you could do. One is that you could apply ratio test directly. That's always a good test because, so maybe I should note, I'm gonna let you ask this. So ratio test, if you can get a conclusion from it, it's, when you apply ratio test, it always tell you it's absolutely convergent or divergent or inconclusive. So you can just apply the ratio test directly at first to get absolutely convergent, but you may get inconclusive at some point, right? So that doesn't help if you get inconclusive, but it's always a good approach to try. And I'm not going to take that approach because I think you can all use ratio tests at this point. What I'm going to do is I'm going to use a definition of absolutely convergent. So for a series to be absolutely convergent, we must find the series of absolute values. So that's a series absolute value -1 to the n minus 1 divided by square root of n. So we want to know if this series is convergent. If it is convergent, the given series is absolutely convergent. That's a definition. So is this convergent? I don't know. Let's find out, right? So take this series with absolute values. So that's a -1 to the n minus 1 divided by square root of n. And that will becomes, and when we take the absolute value of -1, as we talked about before, that just become +1, right? Just 1 over square root of n. And the 1 is positive, square root of n is positive or 0. In this case, n from 1 to infinity, so square root of n is always positive. So we can just drop the absolute value. So that becomes sigma n from 1 to infinity, 1 over square root of n. And that you can write as sigma 1 over n to the 1/2. And from here, we don't use, you can try to use ratio test, but I'm not. I'm just going to use the p-series test, because that's the 1 over n to the p. From p-series test, we know that p is equal to 1/2, which is less than 1, and it's going to be divergent. So this series, when we apply the p-series test, is divergent. That means the one with the absolute value that I'm interested to find, this part is divergent. If the series with the absolute value is divergent, that means the given series, this one that's given, without the absolute value, is not absolutely convergent. Well, we at least, so that the good thing is that we exclude one of the options, right? We get 3 options at the beginning: conditionally convergent, absolutely convergent, or divergent. So now we find out that it's not absolutely convergent. So we get rid of one of them. But is it conditionally convergent? That's the next question. Means that, is it convergent? Well, let's find out if it's conditionally convergent. It's a alternating series. So that means we can use alternating series test. Right? There's a few, there are 2 parts that we have to show, but we need to know what Bn is from the given series. So I'm going to take the series, I'm going to rewrite it as -1 to the n minus 1 times 1 over square root of n. Again, n from 1 to infinity. And in this form, this is what we call Bn, which we need. In order to use alternating series test, we have to test the first condition, limit n goes to infinity of Bn, 1 over square root of n. What is the limit? Well, if n goes to infinity in the denominator, the numerator is always 1, so that fraction is going to approach 0. So that's actually a good thing, right? Because we want the limit as n goes to infinity of Bn to be 0. That's the first condition. The second condition is that we need to know if it's decreasing. So we need to find a Bn minus Bn plus 1, or the other way around. It's up to you which one goes first, as long as you know what the results tell you. So that will be 1 over square root of n minus 1 over square root of n plus 1. And if we common denominator, we get square root of n times square root of n minus 1, sorry, n plus 1. And in the numerator, we have square root of n plus 1 minus square root of n. And is this positive or negative? This part is positive, I know. This is also positive. So the denominator turns out to be positive. What about the numerator? I know that the first part, square root of n plus 1, is bigger than the square root of n, right? As the n increases, we always end up with a bigger value when we take a square root. So that means the numerator is positive. We get a big number minus a small number. So bn minus bn plus 1 is positive. Therefore, bn is greater than or equal to bn. In this case, it's strictly greater, but it doesn't matter. Okay. We can just write as bn greater or equal to bn plus 1. So the second condition is satisfied using alternating series test. Well, both conditions are satisfied. Therefore, this series that I want to know if it's convergent, and I found out that because both conditions are satisfied, therefore the series that I'm interested in, oh, this one does the same. This series is convergent. But the absolute value of this series is not convergent, right? That's what we did the work earlier. The absolute value of that series is not convergent. But the series itself is convergent. Therefore, it's what we call conditionally convergent. Sorry, and I think n minus 1 there. Since this series is not convergent, but the series without the absolute value is convergent. So we say the series without the absolute value is conditionally convergent. And if we find out that it's conditionally convergent, there's no need to test for divergency because it's already conditionally convergent. It's not going to be divergent because it's already convergent.
Thank you.
Yeah. I didn't try to use a ratio test. If you apply the ratio test directly, because the ratio test tell you whether it's absolutely convergent or divergent or inconclusive. And I believe this specific example, if you try to use a ratio test, you're going to get inconclusive if you try to use a ratio test in the beginning. I mean, the work we did shows that it's not absolutely convergent, it's not divergent. So it's conditionally convergent. The ratio test doesn't tell us that. Good question. Any other questions? Oh, before I move on to someone else's question, I just want to point out that if you use root test, the result is also going to be the same. So the root test will also going to be absolutely convergent, divergent, or inconclusive. Just like the ratio test, they give you those three results. What time is quiz? Well, whenever you guys are ready, we can take the quiz. I just want to make sure that any final questions are answered before you start working on the quiz. The quiz, again, just like before, you're going to get half an hour on the quiz and then 10 minutes to upload your work. If you don't have extended time, if you're not sure how much time you have left, feel free to ask. Some of you are already doing that, which is perfect. But definitely keep track of the time. Any final questions? Okay. Before I give you the quiz, this is what I'm thinking. I'm gonna give you so this week, I think it's Saturday, we're gonna have a homework due, right? And then I'm gonna give you another homework assignment that's due Thursday, this coming Thursday. And after that, I'm gonna give you another homework, the very last, so let me write down this. So homework, what was it? Homework 8 is due Saturday, I believe, right? And then I'm gonna give you homework 9. This will be officially the last homework, which is due, I'm thinking about next Thursday. But after that, I'm gonna give you an optional homework. Let's say the homework, it's not gonna be a lot. It's gonna be about, I'm thinking about 20 points also. This homework that will be due the Sunday. So let's just see next Sunday. Everything has to be done before that. So that will be optional homework. It's up to you if you want to work on it or not, but just, let's say you feel like you need a little bit more a boost in your grade. You can work on that optional homework. If you already have 100% on the homework, 100% on the quiz and everything, you don't have to do the homework, the optional one. Right? But if you feel like, if you feel like one quiz, remember that one quiz will be dropped as well. The lowest grade on the quiz will be dropped. But if you feel like, you need a little bit, extra, I don't know, more points to improve your grade, that's something you can work on. So that's my plan. Keep that in mind. Anyway, any final questions before today's quiz?
Yeah, I guess just I still don't understand. Like, if you do have 100% on the homeworks, like it is gonna benefit you. Like, I obviously don't have 100 on the quiz and tests. Like, I'm just asking if you do this homework, will it like benefit you even if you have 100 on all your
Yes,
homework?
it will benefit you because when I'm putting together the final grade, I'll consider the fact that you work on the optional homework and I'll look at how well you did on that optional homework.
Okay, thank you.
I don't have a specific formula that I'm going to use, but it will help. All right, so just keep that in mind. So if you see, lots of homework coming up next week, don't panic because only one officially that's due next Thursday. So this will be the officially last homework. The other one is optional. On the final grade is going to be curved. Not that I'm aware of.